So the net change theorem is really, really important to what we do um, in this half of calculus because we're going in and we're using the antiderivative, the integral, to analyze some situations where we may have the velocity of an object, and we want to find the displacement and how far it moved, right? So that's what the net change theorem is going to help us do. Um, we're going to understand the net change theorem, find the displacement of a particle given its velocity. We're also going to find the distance traveled by an object. So there are these two competing concepts here: the net change or the displacement, and also the total distance traveled. So we're going to talk about those as we go into this PowerPoint. And let's just really kind of focus at the beginning on what it is we're finding. When we talk about the net change theorem, what we're using the rate of change of an object to make a statement about the total change. Okay, so it says when a quantity changes, the new value equals the initial value plus the integral of the rate of change of that quantity. Okay, and that's what we have here. So the new value equals the initial value plus the integral of the rate of change. All right, so one consequence of an integral is that we take a function and we find out what we took the derivative of to get that. Okay, now if you recall back when we were studying derivatives, to get from the position of an object to its velocity, we took the derivative, and to get from the velocity to the acceleration, we took a derivative. But if I had the acceleration and I wanted to come up with the velocity, I would have to take the integral or the antiderivative. And the same thing, if I had the velocity and I wanted the position, I would take the antiderivative. So that's really what we're saying here, that if I have the rate of change, I can take the antiderivative of it and find its position, or really more importantly, its change in position. Okay, that's really what we're going to be finding, the change in position for that object. Okay, so let's take a look at some problems here. In this one, we're given the growth rate of a tree. It's given to be x squared, and the tree's initial height is 0. Find the tree's height after 4 years. So the height after 4 years, and this is rather small, I'll work it out a little larger here. The height after 4 years is going to equal this thing, plus the integral from a to b of f prime of x dx. All right, so in this case, we're looking for the height after 4 years, and that's going to equal the initial height plus how much that height changed over those 4 years. Now, we said that the initial height was 0, so we're just going to have 0 plus x to the third over 3 evaluated from 0 to 4. And that's going to give us that height after 4 years. So if I plug 4 in for x, I'm going to get 64, and 64 over 3, let's see, it turns out to be about 21.3 feet, right? So I could work that out on a calculator, 21.3. If I plug 0 in, I'm just going to get 0, right? So that's why we're just figuring on the 64 over 3. So what we found is that tree, the height grew 21.3 feet over those 4 years. And because the initial height was 0, that change in height is the actual new height. What would have been different right here is, imagine that the initial height of the tree was, 6 feet, right? So then I would take that 21.3, that's what I get from right here, and I would add that to the 6 to get the new height after 4. So in the event where our initial height is something other than 0, right, we would have to work that problem slightly differently. Okay, so here's another problem that is just like the one we just finished doing. You can take a look at that one on your own. Given the growth rate of a corn stalk, right? So the growth rate of the corn stalk is e to the x. It's measured in inches. What is the corn stalk's height after 5 weeks? So we're gonna go in and find out the integral from e to the x dx. The integral of e to the x is just e to the x. So we're going to have e to the 5th minus e to the 0. E to the 0 is 1. Okay, so we'll have e to the 5th minus 1. And working that on the calculator helps us figure out that that is 147 inches, okay, after 5 weeks. The net change has several applications that we want to make sure we discuss, and we'll look at another PowerPoint, another video here in a few minutes where, or I guess maybe in a couple of days for you, where we talk about some of those applications. But one of those is in finding the net displacement of a particle. So what I want to show you is that imagine we have a particle, and at time 0, at time equals 0, that particle begins moving to the right for 3 seconds, and then it comes back to the left. So the net displacement is this distance, the distance from where it started to where it ended. This is what we refer to as the displacement. Now that is different than the total distance traveled. The total distance traveled is this red line plus the other red line. But the displacement is the difference in where it began and where it ended. And this formula will give us that net displacement. If you look at this problem, we're given the velocity v of t. Okay, velocity is equal to 3t minus 5 for a particle in motion from time equals 0 to 3 seconds. And we want to find the net displacement. So to find the net displacement, I'm going to integrate from 0 to 3 of 3t minus 5 dt. The integral of 3t is 3 halves t squared minus 5t. And we're going to plug in 0 and 3. So when I plug in 0, I just get 0. That's where this guy comes from. And then you can see where we have evaluated this thing at 3. So it turns out that our net displacement is negative 3 halves meters, right? The problem was given in meters, so the displacement is negative 3 halves meters. So what does it mean to say the displacement is negative 3 halves? Well, if you look at a graph of what we had, okay, so here's a graph of the velocity, 3t minus 5. Because the displacement is negative, right, we know that this object ended up either below or to the left of its initial position. Okay, so if it's moving along a straight line, then it would have ended up to the left of the initial position. Notice these blue areas. Okay, so this blue area that I'm highlighting in red seems to be a bit bigger than the one that I'm highlighting in green. Okay, so it may not be exactly obvious, but if you look closely, you'll see that the one that's highlighted in red is a bit bigger. So because the one in red is a bit bigger, there's more negative displacement than there is positive displacement. So in fact, this is an object that began, we'll just say it began here at 0. It moved to the left for almost 2 seconds. And then it came back toward the right. And the displacement is the difference between where it started and where it stopped. In this case, that is negative 3 halves. Okay? So the negative sign just indicates that it stopped to the left of the initial position. The 3 halves indicates how far it was from that initial position. Here's another problem where we have a particle moving along a straight line, and we want you to find the net displacement. You can follow the math here and figure out that the net displacement was 9. Okay. Another problem, that what's different about this guy is that our velocity is 2 square root of t. Remember, 2 square root of t is 2 times t to the 1/2. So if I said to find the antiderivative of that, you would have 2t to the 3 halves over 3 halves. And to resolve that fraction on the bottom, we're going to multiply by its reciprocal. So if you're wondering where on earth did the 4/3 come from, it comes from this. Okay. So we can evaluate, we can plug those numbers in. We've looked at how to do 4 to the 3 halves a couple of times, right? You've got 4 to the 3 halves right here. This just means the square root of 4 cubed, which we know to be 8. Okay. And then so this is all just 8 times 4/3 is 32/3. So we mentioned